So to end off this video, I want to briefly discuss a couple of geometric linear transformations in the real vector space R2. The first one we're going to talk about is called the dilation or contraction operator. And for this type of linear transformation, every vector gets sent to a multiple of that vector. So for example, if k happens to be greater than 1, then it's going to be a stretch of our original vector v. If k happens to be between 0 and 1, then it's a contraction of our original vector. And there are a couple other special cases when k is equal to 1 and when k is equal to 0. If k is equal to 0, we're just going to get the 0 transformation that we already saw. And if k is equal to 1, we get something called the identity transformation, which you'll see on the worksheet. Another type of linear transformation we might see is a reflection operator. This is going to happen when t sends an ordered pair to an ordered pair where one of the components gets multiplied by -1. So in this particular example that I've drawn out for you, our x component gets sent to -x. So we have a reflection over the y-axis. If y was sent to -y, then we'd have a reflection over the x-axis. Next up we have what are called orthogonal projections. So if we have a map where one of our components gets sent to 0, then this is a projection on a certain axis. So for example here, if our ordered pair, if y gets sent to 0, this is a projection onto the x-axis. If we had x being sent to 0 and y being sent to y, then it would be a projection on the y-axis. So what I want to do is end off the video just showing you a proof of why these projections are linear transformations. So what I'm going to do is I'm going to take two elements inside of R2, I'm going to label them V1 and V2 just for notation's sake, and we're going to show that this map satisfies both properties 1 and 2. So if we do t of V1 plus V2, what does that equal? Well, what is V1 plus V2? That's going to give us the vector A plus C and B plus D. What does t do to this vector? It projects it onto the x-axis. So it sends this component to 0. So we're going to be left with A plus C and 0 as our second component. So let's evaluate this expression next. How does t work on this vector up here? Well, by definition, t sends the second component to 0. And it's going to work in a similar way on this vector up here. It's going to send that second component to 0. And we can add up these vectors, and we're going to get A plus C and 0 as that second component. So you can see that these two expressions are equal. So t satisfies property 1. Next up, what we're going to do is we're going to take k as a real number and we're going to check the second property. Now the reason I've chosen k here is because I already have an entry as c inside that second vector. So let's check and see what happens when we evaluate t of k times v1. So first of all, what we're going to do is we're going to try to figure out what this vector looks like first. So I got to work inside the brackets here. So remember, v1 is a, b. So here's k v1. Now we can apply t to this vector here. And when we apply t to this vector, we end up losing all the information in the second component. So we project it now onto the x-axis. And second, what we have to do is we have to evaluate this expression, k times t of v1. Or this is the same thing as saying k times t of ab. So here now we can apply t to this vector first. We're going to lose that v component. So we're going to get k times a0. And then now we can multiply the k through. So we're going to get ka and 0. So it is true that t satisfies property number 2. fact t will be a linear transformation from R2 to R2.